Today we're going to look at trig functions and parametric equations. So in trig functions that are used for parametric equations, we use theta as a parameter. Okay, so we're going to use theta as a parameter, and to do that, what we're going to do is we're going to write the equation in terms of theta. So my x value, let's just use this for an example, would be x equals 2 cosine theta, and y is equal to 4 sine theta. Now, just like trying to move parametric equations, convert them from parametric to rectangular, we're going to do the same thing here. We're going to try and get rid of the parameter, right? So to do that, let's solve for the trig function first. So let's do this one first. We're going to do x first. I'm going to solve for cosine theta in terms of x. So I end up with cosine theta equals x over 2. And in the other function, I end up with sine theta equals y over 4. Okay, so those are my two functions. Now, to get rid of the parameter, I need to substitute those in to get some value. So we do know a Pythagorean identity that will allow us to do that, right? If I use cosine square theta plus sine squared theta, and make it equal 1, and I substitute in, for cosine, I substitute in this x over 2, and for sine, I substitute in this y over 4, I can make this calculation, right? So I'm going to do this, x over 2 squared plus y over 4 squared equals 1. Go ahead and do your calculation. So it ends up with x squared over 4 plus y squared over 16 equals 1. Okay, and so if you've been remembering what we've been doing earlier this unit, what you can look at too is that this is the graph of what? This is the graph of an ellipse, right? This is an ellipse. Okay, and so this is an ellipse with a center at 0, 0. Now, one thing I know that some of you guys are going to want to know is, what about this parametric equation here, or I'm sorry, this equation here, this identity, right? Am I always going to use this identity? And the answer is, yeah, really you are. As long as you can solve for cosine and sine in terms of x and y, you will use those identities, this particular identity, I'm sorry, to calculate this equation for the rectangular equation. So it's not a function, but it is an equation for an ellipse. The other thing we're going to look at today is projectile motion. Okay, projectile motion. So a projectile motion equation is used every time that you launch something at an angle that's not 90, right? Anything that's not 90. So anything that's not perpendicular to the ground, this set of parametric equations is used for all projectile motion problems for now. Okay, these are what we're going to use for now, and you will need to memorize these, so please make sure that you do that. So x is equal to t v sub 0 cosine theta. Okay, and y is equal to t v sub 0 sine theta minus 1/2 gt squared plus h sub 0. Now there's a lot of terms here that we've got to actually make sure that we can identify. So v sub 0 is initial velocity, right? It's the speed, the velocity, speed and direction of the object when it's first launched. Okay, g is the gravitational constant. Now, the gravitational constant is going to be dependent upon whether or not you're using metric units or English units. The gravitational constant in metric units is 9.8 meters per second squared, and the constant in English units is 32 feet per second squared. Okay, and yes, you are going to have to know those values. T is time, and that's our parameter. Okay, and h sub 0 is your initial height. And your theta is the angle of the motion. Okay, angle of motion. And so when we're doing a problem with these particular values, I will expect you to be able to use these values. Given other values, you should be able to solve for the remaining values. So let me give you a problem, okay? And we will solve this together. Let's suppose, and you're just going to have to live with my drawing here, okay? There's a basketball hoop. And it is 10 feet off the ground. Okay, so from here to here it's 10 feet. Okay, over here is a person, and she's making a shot, and she is situated herself 13 feet from, that's supposed to end up here actually at the basket rather than all the way under the pole. Okay, she's 13 feet from the basket. Okay, so that's to right here, which is right under the basket, to the center of the basket, really, is what we're aiming for. And then she's going to release the ball 4.75 feet, okay, when it first leaves her hand, all right? And what she's going to do is her initial velocity, they tell us, is 24 feet per second, and she's traveling at an angle of 53 degrees. Okay, so I have a ton of information here. What I want to know is, does she make the shot? Now, this shot is a perfect swish shot. Okay, she's not going to hit the rim. She's not going to hit the basket, right? This is a perfect shot. So we're looking for ideal shot here. Okay, so remember our equations. X is equal to T V sub 0 cosine theta. Okay, and Y is equal to T V sub 0 sine theta minus 1/2 GT squared plus initial height. Okay, and so what we're going to do here is we're going to see if she makes this shot. And to do that, what we need to do is figure out if she achieves the horizontal and the vertical distance at the same time. We want them to be equal to each other, right? Because she has to achieve the horizontal distance of 13 feet at the same time that she achieves the vertical distance of 10 feet so that that ball goes into that basket. Okay, so the first thing we're going to do is we've got to solve for T, and we're going to do that using this Y equation first, okay, because we know enough information to do that. All right, so using what we know, all right, Y is equal to T times the initial velocity, which we said was 24, times sine of the angle, which is 53, minus 1/2, we're working in feet, so my gravitational constant is 32, times squared, okay, plus 4.75 is my initial height, because that's where she is when she releases the ball. Okay, now let's go ahead and work that out. All right, and so you have a couple of ways of doing this. I would recommend that you use your graphing calculator. Okay, graph your equation. Okay, make sure that your calculator is in degrees. Graph. Okay, and so here's what's going to happen. Okay, graph this equation and graph the equation y equals 10. Why am I choosing y equals 10? Because that's where this ball hits the vertical distance, right? I want to know t at y equals 10. Because what I want to know is where does this ball, at what time does this ball get high enough to reach that distance? And so to do that, I need to make it y equals 10. So graph the two equations. Graph y equals 10 and graph y equals t, y equals t times 24 times sine 53 minus 1/2 of 32 times t squared plus 4.75. Okay. And then use the calc function on your calculator after you've graphed them both, and do calc, and then go to intersect to see where it intersects at 10, and then write down your t, right? And so when you graph it, in my my calculator tells me that the value is about 0.774. Okay. So now I know that t is equal to 0.774. So now what I'm going to do is I'm going to take this t value, okay? I'm going to take this t value, and once I get this t value, okay, what I want to do is once I get this t value, what I want to do is I want to take that t and I want to put it into my x equation. And my goal is to take this t, okay, put it into my x equation. Wow, that's convoluted. I want to put it into my x equation, and I want to know if it will clear this 13 feet. I want to know, is this t going to give me enough horizontal distance to clear 13 feet. Okay, so to do that, I'm going to put in x equals 0.774. My initial velocity is 24, and I'm going to take cosine of 53, and I get somewhere in the neighborhood of 11.1 feet. So the answer is no, the ball won't make it, right? The ball's actually going to land a couple of feet short of this basket. Okay, so when you're doing projectile motion problems, make sure you take into account all of the different pieces, your gravitational constant, and then you will use your graphing calculator.